All right, here we go. We got part two of the cardiovascular system. Sorry about the abrupt ending to part one, but I had kind of lost track of time. Didn't realize it gone on 20 minutes. It's way longer than I wanted, so let's just rock and roll part two. We're getting into the actual cellular level. We're going to start talking about the cardiac muscle cells, how they differ from skeletal muscle cells, possibly how they differ a little bit from smooth muscle cells, but let's talk about the characteristics. Cardiac muscle cells are actually relatively small. When you think about skeletal muscle cells are extremely long, multinucleated, many mitochondria. Cardiac muscle cells, on the other hand, are small and they contain one centrally located nucleus. So an immediate difference between the two is skeletal muscles multinucleated, and cardiac muscle tissue and muscle cells have a centrally located nucleus, meaning the nucleus in the middle. They are arranged like or similar to skeletal muscle fibers in the fact that they have striations, but the skeletal muscle system, extremely long banded striation cells where they one laying on top of each other, kind of looking like rows or the lanes of a road stacked one on top of another. Whereas skeletal muscle fibers have more of a woven look to them. There's almost like it appears to be spacing between them. The contraction method is very similar in the fact that they have to be stimulated by an action potential. There's a changing of ions and chemicals just like there is in the skeletal muscle system contraction, where they have sarcomeres. The sarcomeres shorten, you have the myosin heads, you have the ratcheting action. The difference is how that operates as a whole. Another similarity to skeletal muscle tissue is the fact that cardiac muscle tissue contains a lot of mitochondria. You have to really not think about this hardcore, but it should seem fairly obvious. When you use your muscles a ton, they require a ton of energy. Your skeletal muscles can reach fatigue. When they reach fatigue, that's basically the point where no more energy exists in the form of ATP for those cells to function at a normal level. So, cardiac muscle tissue has the same situation. They have lots of mitochondria, so they can generate tons of ATP, except for your cardiac muscle cells do not reach fatigue status. This should seem like a fairly obvious reasoning here. If your cardiac muscle cells reached fatigue status, you would die. If your cardiac muscle cells start reaching fatigue, they no longer contract efficiently. If your heart does not contract efficiently, you don't pump nutrients throughout the body, and the tissue ceases to exist. This should seem fairly obvious when the heart attack occurs. A heart attack, clogged artery, clogged vein of the heart, tissue starved of nutrients. No nutrients, they don't function. If they don't function, your heart does not pump, you end up with a heart attack. So they contain a lot of mitochondria, except for they don't reach fatigue status like skeletal muscle tissue does. If you take a look at this, you'll notice that, yes, they are striated. Yes, they have a large centrally located nucleus in the middle of the cells. But you'll notice they aren't extremely stacked tightly on top of one another. There is a small amount of spacing between them, so it has almost like a woven look to it. Here's a drawing of that exact same thing. The defining feature between skeletal muscle and cardiac muscle is the fact that cardiac muscle tissue has intercalated discs. That's huge. The reason it looks like there's spacing here is because there is like a collagen and elastin network, which we'll get into in just a little bit. But keep in mind, intercalated disc presence indicates cardiac muscle cells. So what that intercalated disc is between them, it's kind of like a membrane that interlocks the adjacent cells. This has huge benefits for the cardiac muscle tissue. What it does is you get a sharing. Sharing is caring, of course. So if the ions and materials can be shared between all of the cells within that cardiac muscle tissue, you get an allowing of action potential that allows to travel very quickly throughout the entire heart muscle tissue. That's important. A slow contraction rate will result in slow or inefficient pumping, which no nutrients will get around to the body. Boom, dead. Okay. It also increases the efficiency of the cells. If they have that intercalated disc connecting between them, they can all pull together. Think of this like a tug of rope team. If each member of the tug of rope team is an individual cardiac muscle cell, when everybody pulls at the exact same time, you generate more power. It's a more efficient system than people pulling at different times on the rope. All right. The next little portion we're going to go over is your heart actually has this fibrous skeleton to it, and it's mostly made of collagen and elastic connective tissue. Connective tissue, keep in mind, connects things together. What this does here for you, it provides a support, a framework. It adds strength and prevents overexpansion of the heart. That's really important because your heart contracts and it fills with blood and expands, and then it contracts again and forces blood out. If you had overexpansion, you would have ripping and tearing of muscle tissue. That ripping and tearing of muscle tissue in your heart would kill you. So that connective tissue provides that support for it. What it also does is it allows the heart to return to normal shape after contractions. This is where those elastic fibers come into play. When your heart contracts, it squeezes them together, and then when it expands, that elastic allows it to stretch, but then brings it back to its regular shape. This is important in certain disorders. Things like, you've heard of people having an enlarged heart, or if you are in biomedical science, you will know that Anna Garcia has hyperventricular or left ventricular hypertrophy. What that means is her left ventricle of her heart is oversized. When the muscle tissue becomes oversized, you get added stress put on those elastic and collagen fibers. It's like a rubber band. If you stretch it too much, it's going to break. That actually occurs when people have oversized hearts. Oversized heart, too much stretching, get it stretched, breaks, your heart stops working. So an oversized heart or hypertrophy of certain ventricles or atrium of the heart actually causes a lot of problems further down the road. The other thing that fibrous skeleton does is it stabilizes the position of valves. This is where the chordae tendineae come into play. Think of it like a rope system. When you pull on the rope, it opens the valve. When you let loose the rope, it closes the valve. The chordae tendineae are attached to a specific set of muscles within those chambers of the heart called papillae, or papillary muscles. But if you're looking at this right here, this would be your tricuspid valve, this is your bicuspid valve. You have the chordae tendineae that attach to the muscles. Those muscle attachment sites pull the ropes, opening the valves, but it also stabilizes their position. This is a big factor in preventing blood from flowing backwards from the ventricles into the atriums. That's important though. You want those valves to be a one-way door. Whenever you have malfunctioning valves, you end up with like heart murmurs, and blood can flow backwards. That reduces the efficiency of the pumping, the flow of nutrients. Again, a bad situation for you. Okay? So the last thing we're going to get into here is the heartbeat itself. You have to understand that when your heart beats top, then bottom, top, then bottom. What I'm talking about is your atriums will contract first and push all that blood down into the ventricles, and then the ventricles will contract and push all of that blood out of the heart. It doesn't beat left side versus right side, it beats top atriums, then bottom ventricles. Atriums, ventricles, atriums, ventricles. That is done through the use of two types of cells. You have your contractile muscle cells, which actually contract to force blood out of those chambers into the next area. But you also have what are called conducting cells. These are specialized cells that control and coordinate activities of the contractile cells. Essentially, what it is your heart has its own electrical system that generates action potentials to tell the heart when to contract at specific times. You do not want the atriums and the ventricles contracting at the same time. There has to be a pattern to it. If the atriums and ventricles contracted at the same time, blood would go nowhere. So the atriums contract, pushing blood down into the ventricles, then the ventricles contract, pushing blood out of the heart. How does this work? Well, you have this conducting system that controls the contractile cells. Almost all of the contractile cells of the heart are made of cardiac muscle tissue. The contraction is based on action potentials very similar to that of skeletal muscle. And if you remember correctly, when we did the graph of the skeletal muscle kind of showing the electrical activity involved in action potentials and stimulation of muscle cells, you have that stimulus, you have the fact that it reaches threshold, you have depolarization of the cells, and then you have repolarization. The difference between those two, however, is the fact that you have a very prolonged or extended plateau where calcium is entering and extends contraction time in skeletal muscle tissue. You want that because when you move your muscles, you want to extend the contraction time, so you end up with an influx of calcium and a change in electrical activity. However, in cardiac muscle cells, in cardiac muscle tissue, you don't want extended contraction time. You want an exact amount for it to squeeze blood from the atriums down to the ventricles and from the ventricles out of the heart. So you end up with a difference in the graphs. Here you're going to end up with, this is the heart, and this is in fact skeletal. Okay, so let's talk about the conducting system now. We've talked about the contractile cells. Let's talk about the conducting system. It's a network of specialized cardiac muscle cells that essentially initiate and distribute action potentials throughout the heart. Those action potentials' sole job is to stimulate the muscle tissue, the contractile cells, causing them to contract and actually push blood around the body. There are two types of cells. You have what are called nodal cells and you have conducting cells. Nodal cells are your pacemaker cells. They establish the rate or pace of contraction, and the conducting cells distribute the stimulus. So it's essentially like having two bosses and they're telling people when to do things. Nodal cells, their sole purpose is they depolarize spontaneously, but spontaneously at a specific pattern. And by depolarizing spontaneously, they generate an action potential. And those action potentials occur at regular intervals. You would recognize this as the double sound of your heart, the doo 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 doo. That sound is not the depolarization of the nodal cells. What it actually is the valves closing. But if you notice, it's at regular intervals. The valves will not close unless cardiac muscle tissue contracts. Those nodal cells are depolarizing spontaneously at regular intervals that create the pattern of a heartbeat. So, let's say those nodal cells depolarize, and what happens is when that action potential, it sweeps through the conducting system. So the nodal cells generate the action potential, and those conducting cells actually spread it throughout. And it sweeps across those cardiac muscle cells, generating a contraction. And that's what actually determines your heart rate. So when you have the nodal cells depolarizing at a faster regular interval rate, you end up with a faster heartbeat. Slower heartbeat. There are two groupings of nodal cells. You have the sinoatrial node, which is always called the SA node. It's going to be located in the upper right atrium, upper right back wall of the atrium. And then you have what's called the AV node. It's on the floor of the right atrium near the coronary sinus. These are the concentrations of nodal cells that generate spontaneous action potentials, but they don't do it at the same time. If they generated spontaneous action potentials at the exact same time, you would end up with atriums and ventricles contracting at the same time. So, if you remember correctly, I told you guys that we wanted atriums to contract first, pushing blood down into the ventricles, and then we want the ventricles to contract, pushing blood out of the heart. So what happens is that SA node is going to be the first thing that develops the spontaneous action potential. When it does that, it sweeps across the conducting cells to both atriums, causing them to contract and push blood down. Now, as that signal sweeps across the atriums, it's eventually going to reach the AV node. The timing here is so unbelievable. Once it reaches that AV node, the atriums are done contracting, but that causes the AV node to spontaneously generate an action potential, which sweeps down and across the ventricles, causing them to contract. And the cycle repeats itself over and over again. So if you take a look here at a cross-section of the heart, up here is going to be your SA node, and down here is going to be your AV node. If you notice, this is really, it doesn't have the conducting system reaching the atriums, but this is more of a diagram to produce or show the conducting system of the AV node. So first you get an action potential generated in this concentration of nodal cells right here. That causes a sweeping action. You like sound effects? Those are official. Which sweeps across and causes everything up here, muscle tissue-wise, to contract. Once that occurs, you get that sweeping action. One section of that sweeping action, the conducting cells, reaches the AV node. When that occurs, you cause a spontaneous generation of action potential by the AV node, which follows the arrows that you see right here. So it sweeps down through the bundle of His and then sweeps down into the bundle branches. Those bundle branches then sweep down to the apex and turn into what are called Purkinje fibers. You notice the Purkinje fibers are spread all throughout the walls of the ventricle, and you will notice that the AV bundle, or the bundle of His, and the bundle branches sweep down the interventricular septum. Also notice that some of these connect to papillary muscles, which connect to chordae tendineae. Keep in mind, those help direct or control the valves. The SA node is known as the pacemaker of the heart. If that SA node, or the sinoatrial node, the first one that's going to contract, is not functioning correctly, you don't get proper functioning of the AV node. So what happens is, over time, if pacemaker cells become worn out, die, or start malfunctioning in generation of action potentials, you end up with irregular heartbeats. If they suspect that irregular heartbeat of occurring, what they actually do is they do an EKG. Once an EKG is done, it generates a graph showing the electrical output of the heart. The electrical output of the heart is looked at, and you say, well, we've noticed you have some spontaneous firing of the AV node, or maybe you have a gap in time between the firing of the SA node that results in an irregular heartbeat. In severe cases, they will put a pacemaker on the body, or in the body, which takes control of the SA node and causes it to generate action potentials at regular intervals. So, let's rewind and go through these steps of the conducting system. So the first thing that has to happen is that SA node depolarizes and begins to send a stimulus throughout the conducting system, reaching through into both atriums. Once that occurs, that stimulus spreads to both atrial surfaces, but also reaches the AV node. When the atrium's contraction begins, you actually get the AV node reaching threshold. Once that AV node reaches threshold, the atriums are done contracting. That AV node sends that signal down throughout the bundle of His. Now, the bundle of His is the first section just after that AV node. The bundle of His then branches out into two separate branches in the interventricular septum, which becomes the bundle branches. Travels down that interventricular septum, sweeping to the apex, and then it sweeps across and fibrously branches out into what are called the Purkinje fibers. The Purkinje fibers are distributed across the entire ventricular walls. Once that signal reaches them, the action potential is distributed all over the myocardium, or the muscle tissue cells of the heart, causing the ventricles to contract. Once the ventricles contract, that action potential is gone. The ventricles relax, and as the ventricles are relaxing, that's when the cycle starts all over again back with the SA node. Let's watch an animation real quick.
Action potentials originate in the sinoatrial node and travel across the wall of the atrium from the sinoatrial node to the atrioventricular node. Action potentials pass slowly through the atrioventricular node to give the atria time to contract. They then pass rapidly along the atrioventricular bundle, which extends from the atrioventricular node through the fibrous skeleton into the interventricular septum. The atrioventricular bundle divides into right and left bundle branches, and action potentials descend rapidly to the apex of each ventricle along the bundle branches. Action potentials are carried by the Purkinje fibers from the bundle branches to the ventricular walls. The rapid conduction from the atrioventricular bundle to the ends of the Purkinje fibers allows the ventricular muscle cells to contract in unison, providing a strong contraction.
Riveting. What you're seeing here is essentially how the electrical stimulus or signal is traveling from the SA node, which is located right up here, sweeping across the atriums, reaching the AV node, sweeping down the interventricular septum to the Purkinje fibers, causing it to contract. Notice also the action of the valves. opening and closing. Boom. So what this leads us into is actually what's called an EKG. An EKG is a measuring of the electrical output or electrical events of the heart using electrodes placed in specific regions of the chest around the heart so that it can pick up the electrical activities. In class I have these, but we attach them to the arm for obvious reasons. We can't be attaching things to people's chests in class. So if you look at this, you'll notice that it's arranged in a specific pattern. You have what is called the P wave. The P wave is going to be this section right here. Then you have what's called the QRS complex. The Q is the dip right here, the R is the upward approach, the S is the downward. So this whole thing is the QRS complex. Then you end up with a T wave. Each one of these sections is a very specific event occurring in the heart. Atrial depolarization is essentially the contractions of the atriums. If you will notice, not as much electrical activity occurs there because the atriums aren't very big. They don't have to pump it very far. It doesn't take very much contractile effort in order to push that blood down to the ventricles. However, you will notice in the ventricular depolarization, which is the QRS complex, you will notice that there is an extremely large amount of electrical activity. The reason being, ventricles are larger, it's particularly the left ventricle, and they have to generate enough force to push blood to where they need to go. Therefore, you end up with a large amount of ventricular depolarization or electrical activity. Then you have a lag period in the T wave. That is actually the ventricular repolarization. That's the redistribution of ions and everything like that back to the resting potential for the next contractile effort. So again, P. It's the depolarization of the atria and the atrial contraction slightly after the P. The QRS complex. The ventricles depolarize and contraction occurs shortly afterwards. Then you have T, which is ventricular repolarization. Atrial repolarization occurs during the ventricular depolarization, which is why you don't see a wave, because it gets overshadowed by the ventricular depolarization. So, why would we want to measure electrical activity? So we can figure out abnormal patterns of the heart. We want to know what are called arrhythmias. You can have tachycardia, you can have bradycardia, you can have repeated ventricular contraction. If we can identify abnormal patterns, we can identify abnormalities in the heart, which allow us to treat disorders a little better. So if you want to watch some more videos, there are a couple located in my PowerPoint at the very end. You can find that on Schoology. If you have any questions, let me know.